Hey, Algebra 2 honors. So we did some pretty challenging problems in class the other day. Had a few questions from some students. Wanted to go through some of these fairly quickly. And so let's do it. And feel free to fast forward, to any specific problem in this problem set I gave. And the blank document with these questions is in the shared drive. All right, let's get started. So let's solve this polynomial equation. Now, it didn't say, but you're solving for x here. That's the most, that makes the most sense. I should have said that. N and m are considered to be real number constants. Okay, first thing to notice, do you notice this quadratic is the same as this quadratic? So that's a common factor. So 4x squared plus 12x plus 9 times x minus n. And I'm going to subtract this entire other thing over to the other side. I don't want to distribute anything. Awesome. We got 0 by itself. That's always the key. Now, factor. Watch your parentheses here. I'm factoring out the red factor. So I'm left with this. This minus will distribute. This is a perfect square trinomial of the form a squared plus 2ab plus b squared, where a is 2x and b is 3. This would be x. This would be negative x. So I've got x minus 2x. I've got negative n plus n minus m. So I'm left with 2x plus 3 squared, negative x minus m, and equals 0, and x equals negative 3 halves, multiplicity 2, and negative x minus m equals 0, or x plus m equals 0 if I multiply everything by negative 1, and x equals negative m. And that is multiplicity 1, so we don't have to write the multiplicity. If you do, it's not wrong. You can just write, excuse me, for multiplicity, you can just write MULT for short to go faster. So x equals negative 3 halves, multiplicity 2. And reminder, whenever one of the factors has a power of 2 or higher, you need to state the multiplicity of that 0. It's going to be super critical in a future chapter. I'm teaching it to you now. You are responsible for knowing that that's a 0 of multiplicity 2. Also, our textbook calls this a double root. That term is a little bit antiquated and doesn't generalize. So I'm teaching you a term that generalizes, and you will find that in your pre-calc book next year. Okay, got that one done. Combined like terms. Yeah, I know. Not all these are going to be ones that are actually on the test. Not all of these are ones we've talked about before, but I want you to know the pattern. Okay, this is equal to 5x. I know you know that. Well, when it's pi, just think of pi as x, so it's 5 pi. And this is the one that always gets students. 2 root 2 plus 3 root 2. Well, that's just 2x plus 3x. X happens to be root 2. So it's 5 root 2. We're going to need that very soon in a future chapter. And the same thing is true when you're combining variable expressions. So this would be 5 times whatever comes after, as long as the stuff that comes after is the same, and it is. Yeah, you could distribute this and multiply out, but that's the main point I want to make here. Okay, where does it apply in our chapter? Well, exponent properties. This isn't actually exponent properties. This is combining like terms, then exponent properties. So I have 5 times 7n plus 5 times 7 to the n plus 2 times 7 to the n. The variable part is the same, 7 to the n. So I can add 5 plus 2, and I get 7 times 7 to the n. And our exponent property says this is 7 to the 1. So I add the exponents because the bases are the same, n plus 1. Okay, that's it. Now, oops, sorry, go down. Why is that not loading? There we go. Okay. My point on this question was because we've been talking so much about prime factors, students start to forget that not all factors are prime. For example, 12. What are the factors of 12? 1, 2, 3, 4, 6, and 12. Okay, those are the positive factors of 12. We would generalize this in the future and say plus or minus 1, plus or minus 2, plus or minus 3. Because if you divide 12 by negative 4, you still get an integer. So you could write, 4 is a factor of 12 because you can write 12 as 4 times 3. Negative 4 is a factor of 12 in a certain context because you can write 12 equal to negative 4 times negative 3. So if we're factoring over the set of integers, that means we're trying to factor 12 as to an integer times an integer. Okay, now the reason I made this point that we are factoring over the set of integers, and I said, or else the answer is infinity. Well, think about this. How could I factor 6? If we're factoring over the integers, the only ways to factor 6 are 1 times 6 and 2 times 3. And of course, I can switch the order. I can also make all these. I can make it negative 1 times negative 6, negative 2 times negative 3. I won't worry too much about the negatives in this question. I'll keep everything positive from now on. But if I was factoring over the real numbers, there's actually infinitely many ways to factor 6. So I could factor 6 as 6 equals, for example, how about 3 root 2 times root 2? Multiply that together. It's 6. But it's using irrational numbers. I could factor 6 as 6 over pi times pi. Okay, so I'm not going to really need to do that much, but it's true that 6 over pi times pi is 6. But this is factoring with any real number. But in this chapter, we're factoring over the integers. So that's why it limits our factors. Okay, so how many factors does 6x squared y have? If the question was how many prime factors does it have, we would have a different answer. We would prime factorize 6, and we would find that the prime factors are 2, 3, x, and y. But it doesn't say prime factors. It says how many factors does 6x squared have? Well, what are the factors? And remember, what are the factors of 12? It's this whole list. How many of these numbers are actually prime? 2 is prime, and 3 is prime. That's it. But the rest of those numbers are factors. So what are the factors of 6x squared y? Well, here they are. There's 24 of them. Let's assume that clearly 1 is a factor of 6x squared y. Kind of a trivial factor, not usually super helpful, but it's true. What if the coefficient is 1? What are the possibilities for the variable part? Well, x is a factor, y is a factor, xy is a factor, x squared is a factor, and x squared y is a factor. What if the leading coefficient was 2? Well, 2 itself is a factor, and then 2x is a factor, 2y, 2xy, 2x squared, and 2x squared y. And we could play this game for all the different possibilities of the leading coefficient. And you'll see that all the variable parts are the same. And what we end up with is a 4x6 grid. So there are 24 factors of 6x squared y. Next question. What's the greatest common factor of 6x squared y and 14xy squared? Xy to the fifth, sorry. Key, prime, factorize. 2 times 3x squared y. 2 times 7xy to the fifth. I'll do the GCF. And you know what? It didn't ask for it, but what the heck? We'll do the LCM as well. And the GCF is compare the prime factors and take the lower exponent. They both have a factor of 2 in common, both exponent with power 1. So that's what we put. Now, the top one has a 3, the bottom one doesn't. So the GCF will not have a 3. Bottom one has a 7, top one doesn't. So the GCF will not have a factor of 7. There's an x squared here, and next to the first here, take the lesser. X to the first, y to the first. The LCM, compare the powers, take the higher exponent. The LCM is going to have one factor of 2. It's going to have a factor of 3, a factor of 7, x squared, and y to the fifth. Okay. That's it. You can multiply that out, but I don't care. That's fine. All right. So let's let some notation. Let's let the GCF of a comma b and the LCM of a comma b be the notation for the GCF and LCM of a and b respectively. Show that the GCF of 18 and 12 times the LCM of 18 and 12 is equal to 18 times 12. Hint, leave everything prime factorized. This will be a lot clearer that way. Well, what is 18 prime factorized? It's 2 times 3 squared. What about 12? 12 is 2 squared times 3. So the GCF of 18 times 12 times the LCM of 18 times 8, sorry, not 18 times 12, 18 and 12 is equal to 18 times 12. Let's start filling everything in. So what's the GCF of these numbers? Well, it's parentheses 2 times 3. It's 6. And what is the LCM of these two numbers? It is, you know what? Let me change that coloring. Let me make the GCF purple. And let's make the LCM green. Okay, awesome. What's the LCM? It is 2 squared times 3 squared. All right, on the right-hand side, what do we have? We have 18. What was 18? 2 times 3 squared. 12. 2 squared times 3. This is pretty much enough to show what's going on, because some of the powers on 2 is right here. It's 1 and 2. That's 3. Some of the powers over here is 1 and 2. That's 3. Some of the powers over here is 1 and 2. That's 3. And 2 and 1, and that's 3. So we get 2 to the power of 3 times 3 to the power of 3 is equal to 2 to the power of 3 times 3 to the power of 3. That's all there is to this. I was trying to get you to think about factors and prime factors. Let's show the exact same principle, but with the stuff from question 4. I can literally come up here and copy this stuff and bring it down here, and I got everything I need. Let's make that all black, and let's copy it. What is that? That's the LCM. Put parentheses around that. What's this? It's the GCF. Copy. paste, put it up here, put it in parentheses. And that is equal to this. I'll just drag it over. I should have just done that in the first place. Just drag it over. Put parentheses around it. We're done. Let's just double check visually that this makes sense. Okay. GCF, LCM, expression A, expression B. Note that the sum of the powers of 2 on the left, sum of the exponents on the right, same. 1 plus 1, 1, 1. What about x? 1, 2, sum 2, 2, 1, same. Factors of 3, there's 1 over here, there's 1 over here. 7, 1 over here, 1 over here. Factors of x, 2, 3, 2, 3. Factors of 5, 5 plus 1 is 6, 5 plus 1 is 6. This game will always work out like this, no matter what two integers you pick and no matter what two expressions you pick, polynomial expressions with integer coefficients. Okay. By the way, this also justifies why. Suppose you are given the GCF and the LCM. See, and you know one of the expressions, but you don't know the other expression. This looks like one that was on our MCA and on the homework. Let's say we don't know the blue one. Well, you can use this formula to say, cool, multiply the GCF and the LCM together, divide by multiply the LCM and the GCF, or the GCF and the LCM, multiply them together, divide by the expression you do know, and it gives you the expression you don't know. Okay? Multiple ways to do those questions, so do them whatever way makes sense. The rest of these I think are just all solving equations and inequalities, so let's just jam through them. Okay, let's look at this. So the variable is x, we're solving for x, a is some unknown constant. Let's just do an analysis here. Do you notice first thing that there is a factor of x here? There's at least one factor of x in each term. So the first thing we should do is just get everything to one side and factor out any common factors. Always do that. X to the 5th minus 2x cubed a squared plus xa to the 4th. Remember to never divide both sides of an equation by the variable. Always keep everything and factor. We'll factor out one factor of x because that's all these have in common. I get an x to the 4th minus 2x squared, a squared, plus a to the 4th equals 0. This is a special product in hiding. This is a squared plus 2ab plus b squared. And we know how that factors. That factors as, there's a minus. My mistake, minus. We know how that factors, a minus b squared. Well, what's a? A is x squared. What is b in this case? A squared. Let's write that. X, little parentheses, x squared squared minus 2 x squared a squared plus a squared squared. Hopefully the color coding helps you see it. It's a little bit of extra writing to write this out, but it may actually help you go faster and make less mistakes if you take a moment to write something like this before you factor it. If you can do it at sight without this extra step, great. So this would be x squared minus a squared squared, because it follows this pattern over here. All right, inside of here, this is a difference of squares. I'm going to put a bracket around this, and I'm going to factor this difference of squares inside that purple bracket. I don't want to lose track of that square that's on the outside, but I do know that x squared plus or minus x squared minus a squared is x plus a, x minus a. This is all equal to 0, so I get x plus a squared, x minus a squared equals 0. Reminder, this exponent of 2 applies to every factor that's inside of the parentheses, or in this case, inside the brackets. And the brackets are just parentheses. I just put brackets around it to make it visually easier to read. Okay, we've got everything fully factored. I can see the multiplicities because I've written it in the proper way. And I get what? X equals 0. Awesome. X equals negative a, multiplicity 2. And x equals a, multiplicity 2. Done. All right, on to the next. Okay, 8 is a perfect cubed. 125 is a perfect cube. The exponents are all multiples of 3. There's a difference of cubes here. 2 ways to do this problem. You can factor out the common factor first, or you can do the difference of cubes first and then factor out common factors. Either way works. I am a fan of factoring out common factors to begin with. So I notice there's an x to the 3n and x to the 6n. So I can pull out an x to the 3n. I can factor out an x to the 3n. And there's nothing else in common because this is 2 cubed and this is 125. Or sorry, this is 5 cubed. So x to the 3n is factored out. And I'm left with 8 minus 125 x to the 3n y cubed. All right, now this is a difference of cubes. X to the 3n, 2 cubed, minus 5x to the n y all cubed. Okay, verify that in your mind. And we now need our difference of cube formula, which is what? It is a minus b, a squared plus a b minus b squared, parentheses. Let's just fill in everything. A is 2, b is 5x to the n y, a is 2, a is 2, b is 5x to the n y, b is 5x to the n y. Now just simplify everything and we are done. Simplify each factor separately. 2 minus 5x to the n y, 4 plus 10 x to the n y, minus 25 x to the 2n y squared. Done. Double check from my answer key that I haven't made any small errors. Looks good to me. Yep, there we go. All right, on to the next. All right, let's look at number 8. For number 8, it says to expand and simplify. This does not say to factor. In fact, what's given is already factored. It just says expand and simplify. So the whole point of this is to notice this is a minus b squared, but it just looks complicated. A squared minus 2ab plus b squared. You just have to recognize that this is, that a is 2n x to the n, and b is 3x to the n plus 1 y. Let's expand it. So that would be a squared minus 2ab plus b squared. Let's fill in what all those parts are. 2n x to the n, 2n x to the n, 3x to the n plus 1 y, 3x to the n plus 1 y. I just copied a and b down to the general formula, and I just use parentheses instead of a's and b's. Simplify the exponents and you're done. Raise everything to the power of 2. 4n squared x to the 2n minus 2 times 2 times 3 is 12. N x to the n plus 1 is 2n plus 1 y plus 3 squared is 9. X to the n plus 1 all squared is x to the 2n plus 2. Watch out, you need to distribute the 2 to that entire exponent. Y squared. Done. That's it. All right, let's do number 9. For number 9, I've got, it just, by the way, it says factor. So the previous one, we were multiplying out and simplifying. In this one, we're factoring. So this is already simplified, and we need to go the other direction. First, look for common factors. I notice there's a 2, and these are even. And I notice this one has a single factor of x, and this one has a 2n plus 1 in the exponent of x. So I can pull the 1. I can pull one factor of x out, one factor of x out, and I can also factor out a y, and a y from each one. So let's start with that. I can factor out a 2xy. On the inside, I'm left with x to the n. Okay. And then I factored out a 2 from here, so there's a 6. I've got x to the 2n. I've factored out the y. And now the 24 is, I factored out a 2, so there's 12 left. I factored out the x, so it's gone. And I factored out the y, so it's gone. Now, a couple ways to organize this. But if you notice, this is really a hidden quadratic term, and this is a hidden linear term, and this is a constant term. So I can rearrange this, negative 6x to the 2n plus x to the n plus 12. And now it's easier, whenever your leading coefficient is negative, you will make less minus sign errors if you pull that minus out to the front. So we're going to factor out minus 1. 2xy, parentheses, 6x 2n, switch the sign, switch the sign. Cool. Now, minus 2xy, and this is 6 parentheses x to the n squared minus x to the n minus 12. If you can factor this at sight, great. If you want a little help with it, you can let u equal x to the n, and then over here, just on side work or on scratch paper, but it'd be helpful to show your work so that I can see it. U squared minus u minus 12. So I've just rewritten this a little more simply. And if you prefer this method, great. If you want to guess and check it, great. I don't care. Negative, no hearts. Negative 72u squared. Copy the linear term down to the bottom. I need two numbers that multiply to negative 72 and add to negative 1. That's definitely negative 9u and positive 8u. So that means I can split the negative u into minus 9u plus 8u minus 12. And you can rewrite these two middle terms either way. It'll always work out. Factor by grouping will always work now. 3u, 3, 2, 2u minus 3. And then I can factor out a 4. And I'm left with 2u minus 3. Awesome. Factor out 2u minus 3, and I'm left with 3u plus 4. Let's copy that back over to the left-hand side. Equals negative 2xy. I'm going to get two factors here, and it's going to be 2u minus 3, I didn't write u, and 3u plus 4, I didn't write u, because remember, the u's were actually x to the n. So let's just write x to the n back in. And we are done. Although you should check, I notice this is a perfect square. This is a perfect square, but 3 is not a perfect square. I don't know what n is, so no way to know if that's a multiple of 2. This is clearly none of our patterns. We're done. Okay, let's do number 10. This is an inequality. Whenever you have an inequality, move everything to one side. I will subtract the 2x to the fourth to the left. You can also add the other stuff to the other side. I'll just make a point by doing it the slightly longer way. Okay, so we're here. I've written it in standard form with highest power first and decreasing powers going forward. You notice that the leading term is a negative. If you just multiply everything by -1, you can make things simpler and avoid some minus sign errors that have a tendency to pop up. So I will multiply both sides of this inequality by -1. And I get 2x to the fourth plus x to the third minus 28x squared. And still 0 on the right, but I need to flip the minus sign. Okay, so we're here. Next, factor. Common factor of x squared, 2x squared, plus x minus 28 greater than or equal to 0, and x squared. This has to factor as 2x and x, and we just need to figure out what would work out. One of them needs to be negative, one of them needs to be positive. The two numbers here have to multiply to 28. So 4 and 7 is looking good. 2 times positive 4 minus 7 will work, because 2x times 4 is 8x. This is negative 7x. 8x minus 7x is 1x. Negative 7 times 4 is negative 28. So I just factored that one at sight. What are the zeros? X equals 0, multiplicity 2. You don't really need to write the multiplicity when it's an inequality, but it's helpful to just get in the habit of doing it. 7 halves and -4. Okay, make a number line. We now need to, and I recommend you graph it whether it's asked for or not, because I could ask you to graph the solution set. Also, you are less likely to make errors on your interval notation if you graph your solution set. The numbers that matter are -4, 0, and 7 halves. So I just put them on the number line. They don't have to be scaled perfectly. That's okay. First thing, Do the zeros make the inequality true? The answer is yes. Zeros, these are zeros. The zeros, by definition, make this side 0. 0 is greater than or equal to 0. That's true. So my graph is going to include the zeros. The zeros are in the solution set. Now I'll do the longer way of a sign chart. And you want to write out every factor. Okay, I've got x squared, 2x minus 7, x plus 4. If you're clever, you might notice that the x squared is not going to contribute to the answer directly, because x squared is always positive as long as I don't plug in the 0 or 0. Okay, so if I pick any number to the left of -4, this is negative, and you'll find that if I plug in any number between -4 and 0, this is negative. If I plug in a number between 0 and 7/2, like 1, this is negative and positive. Notice the sign of this factor switches at the 0 of that factor. You just got to be careful of whether it starts out negative or positive. This one starts out negative. So I plug in -10, that's to the left of -4, it's negative. When you go past the 0, it switches to positive. Now the product is positive. Positive times a negative times a negative is positive. Negative, negative, positive. What do I want? I want where the product is greater than or equal to 0. So I want this and this. I want where it's positive. So my graph is everything over here. My graph is everything over here. My solution set in set/interval notation is everything from -infinity to -4 inclusive. I've got this single number 0. It's like a singleton set. Sometimes you'll hear people say that. And then I've got the interval from 7/2 to +infinity. And I want to put this solution set all together into a big solution set. So I'm going to do the union of those sets of numbers. There's my solution. Okay, which number was this? That was number 10. Yep. Double checking my signs and everything. Yeah, good. Okay, cool. All right, solve this equation. This is an equation, and we're solving it. To solve it, we just need to factor. I notice there's a common factor of x here. 6x squared minus x minus 2. Okay, careful. Do you see that this is all being squared? So it can be helpful if I'm going to factor inside of here and all the factors are going to get squared. Put a bracket around it and factor inside of here. I notice that a factor of x can be factored out. 4x squared plus 4x plus 1 equals 0. X, now does this factor? Let's see. So this has to be 2 and 1. I need, let's see, I think 2x and 3x, and I would want the 3, excuse me, 3x and 2x, and I want the 2x times 2 to be negative. So this would be a negative and this would be a positive. Let's just mentally check. 2x times -2 is -4x. 3x times this is 3x. -4x plus 3x is -x. And 1 times -2 is -2. So we're good. Now inside of here, I see that I have, this is a perfect square trinomial. 2x plus 1 squared, but this whole thing is squared. One more step, x, 2x plus 1, 3x minus 2, and I've got a factor of x squared because that x is being squared, and this is 2x plus 1. 2 times 2 is 4 equals 0. Combine factors, x cubed, 3x minus 2, and 2x plus 1 to the 5th. What are the solutions? X equals 0, multiplicity 3. X equals 2/3. Multiplicity 1. I didn't really need to write that, but that's true. X equals negative 1/2. Multiplicity 5. In most answer sets, you will see this without the multiplicity written for 2/3. Let's double check there. 0, multiplicity 3, 2/3, negative 1/2, multiplicity 5. Awesome. Let's solve this. Great. Inequality. Do you notice any common factors? I see this x plus 3, and I see this x plus 3. Those are in common. I see a factor of x. I see a factor of x here. There's 2 factors of x, but there's one in common. So that means take all this stuff, move it over to the other side. X squared, x minus 3, 4x minus 3, minus x plus 3, x minus 1. Do not multiply things out unless you need to. If you see common factors, keep everything together. Get 0 by itself, factor out the common factors. Excuse me, that was a plus. X plus 3, x plus 3, x, and an x. So what can come out? X can be factored out. X plus 3 can be factored out. What am I left with? When I'm left with something complicated, I like to put a big bracket around it. It's easier for me visually to keep track of everything. I'm left with one factor of x and 4x minus 3. This factor of x is gone, this is gone, and I've got x minus 1. Can you see why the brackets really help? Because it helps me keep track of everything on the inside, and also this minus, the way I wrote it, this minus, it reminds me to distribute that minus sign. So I get x times x plus 3. Also notice there's no common factors anymore on the inside, so the only thing I can do is multiply this out, combine like terms, and see what happens. I get 4x squared minus 3x minus x plus 1 greater than 0. And x plus 3, 4x squared minus 4x plus 1 greater than 0. And this is x plus 3. This is definitely a perfect square. Okay. Perfect square, 2 times the a and b. And okay, we've got this. What are the zeros? The zeros are x equals 0, x equals negative 3, x equals 1/2. Yeah, there's multiplicities, but that's okay. We don't need it at the moment. Negative 3, 0, 1/2, good enough. Do the zeros make it true? No, because it's greater than and not equal to. Okay, so the zeros make it false. So the zeros are plotted with open circles. All right, so let's look at the sign chart. Now, we could do the longer version of the sign chart and write out the factors. However, we can do a little bit of a shortcut version and just look at this factor. I'll do that in purple. This factor, I'll do that in green. And this factor. I'll do it in blue. But this factor, remember, it comes with the square up there. Okay, so the x factor is negative, negative, positive, positive. What about the x plus 3 factor? It's negative, positive. It switches at its 0. Positive, positive. What about 2x minus 1 all squared? Well, that's always positive as long as we don't plug in a 0, but we're not because we're looking at values that are not the zeros of the polynomial expression. So this is positive, 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 positive. So what is our product? Our product is positive, negative, positive, positive. What do we want? We want where the polynomial expression is positive because we want where the left-hand side is greater than 0. So we come back to here. We graph our solutions. And we just have to be careful that this one value is excluded. I don't even need any of this. I'll just erase it. Done. And we get what? Negative infinity to negative 3, not including that. Union 0 to 1/2, not including 1/2. Union 1/2, not including, up to infinity. There we go. Last one. Solve this. Okay. Couple of ways to do this. I mean, you can kind of think through this in a couple ways. But I noticed this is already factored as a perfect square. And I noticed that this is a perfect square and 25 is a perfect square. So this is 2x minus 5 squared plus. I said this is a perfect square. This is a difference of squares, is what I should have said. Okay, so this is 2x minus 5, 2x plus 5 equals 0. There is a common factor of 2x plus 5 or 2x minus 5 and 2x minus 5. So I will factor out 2x minus 5. And what am I left with? I'm left with bracket 3. There's another factor of 2x minus 5 plus 2x plus 5 equals 0. I can now combine all the stuff on the inside of the bracket. Distribute 6x minus 15 plus 2x plus 5 equals 0. 2x minus 5. 6, 7, 8. What? 8x negative 10 equals 0. 2x, 0 product property. 2x minus 5 equals 0. So x equals 5 halves. Multiplicity 1. And on this one, 8x minus 10 equals 0. Don't know why I slid that down. 8x equals 10. X equals 10/8 or 5/4. Done. Okay, that's the whole review. And this was what we did in class. And these are more challenging. Okay, you're responsible for everything we discussed here conceptually, and some of these would be some of the. It's got some challenging factoring, challenging things to notice. But the numbers are small, so it's doable by hand in relatively short time if you can see the patterns that are happening.